All right, so we're going to look at something that we're going to be doing in lab, or we have probably just started it. But we're going to look at how we can use the ideal gas law, how we can use density, all those derivations that we looked at in the last video, to find the molar mass of a gas or a volatile liquid. That term volatile just means it's easy to vaporize. So it doesn't take much heat to get them to turn into a gas phase. So that's why we can do this on technically liquids because they're easy to heat up and turn into a gas. That's what we mean by volatile. And the way that we do this in the lab is called the Dumas, or Dumas is how it's spelled, but I think I'm saying that right, Dumas method. And it basically, what we do is we put some gas or volatile liquid in a flask and cover it, poke some holes in it just to let atmospheric gases escape. But when we heat it up, what happens is, um, so we heat this up and the liquid inside evaporates and it forces out all of the air so that the only thing occupying the um, uh, the flask is a gas. And so if we know the mass before, so this is here, this is empty, and we know there's some mass, and we know the mass afterwards, then we can start plugging that into our derivations and figure out the molar mass of that gas that's in there or the volatile liquid. So here's our density equation from the last video. Now let's rearrange this to solve for molar mass. Okay, so I moved, the molar mass over, and if I know the temperature and pressure, but how do I know the density? If I don't know what my gas is, like I just can't look that up. How do I know what the density is? Well, what is density? Remember, density is mass over volume, right? Well, let's plug that in. So instead of looking at density, we have mass times R times T over volume and pressure, right? So again, this, how did I get this? That's density right there. And so when I do my experiment, if I know the temperature at which the gas vaporizes, I know the atmospheric pressure around, I look at a barometer, and I know the volume of the flask I use, and then I weigh out my experiment after it's done, I have all of the things that I need in order to solve for molar mass. So let's do a problem like this, and this is going to be similar to what we are doing in lab. So find the molar mass of chloroform if 129 milliliters contains 0.494 grams at 99.6 degrees Celsius and 742.1 millimeters of mercury. Okay, so let's use our equation here. We're going to solve for molar mass. We need to know the mass of the gas times R times temperature over pressure and volume. Okay, so let's say we did this experiment. We weighed our flask at the end of the experiment and found that there was 494 grams of chloroform. And then I know what R is, 0.0821 liter atmospheres, moles, Kelvin, and then my temperature. Okay, well, remember, temperature has to be in Kelvin. So I'm going to take that degrees Celsius at 273.15, and now it is Kelvin. So 372.75 Kelvin. So plug that in. All right, pressure now. Here's my pressure, 742.1 millimeters of mercury. But again, because my constant has units of atmospheres, I'm going to do a quick conversion here. So 742.1 millimeters of mercury. I know that there's 760 millimeters of mercury in one atmosphere. And so that comes out to 0.976 atmospheres. Actually, I got a few more decimal places I could use. Let's take a few more so I can get the right amount of sig figs. 0.976447 atmospheres. And then volume, 129 milliliters. Make sure that that is in liters. So we'll just move that decimal place over a few places. And look at what happens when I start canceling units out. Atmospheres cancel out, liters cancel out, Kelvin cancels out. Look at the units I'm left with. I'm left with units of grams per mole. What is that the unit for? That's the unit for molar mass. So this comes out to, once I put it in my calculator, keep track of sig figs, 120 grams per mole. That is the molar mass of chloroform. In fact, if you want to take some time, chloroform is CHCl3. Just kind of on your own time, like add it up from the periodic table, and you'll see it's going to be pretty close to 120. Why is it not like exactly the same? Because this is not probably not the most the accuracy of our results depends on how high tech or how quality our experiments are. While this method works great in like a general chemistry lab, there's more high-tech ways to do this to get a lot more accurate information, but 120 is pretty close to the molar mass of chloroform.